Morning everyone. My name is Vamsi Krishna, Assistant Professor from Department of Physics, AKNU, Rajahmundry. Today I am going to discuss about working of JFET in negative terminal of gate gate to source terminal, means between the negative potential at between gate and source terminals. Okay. Um, so in previous class I have discussed the I have taught the means potential at the gate terminal will be 0 and with source terminal is also 0. When we increases the potential between the drain and source, so width of the depletion layer will be increases at the bottom, means sorry, at the top end. Okay, means top region, means near the drain region. It will depletion layer will be thinner at the bottom end. Okay, so this is happening due to the this whatever the device is, is in reverse biased condition. The so now we are planning to reduce the uh, potential between the gate and source terminals. So we are giving the negative voltage to the gate and source terminals. So we are keeping the uh, positive voltage at between drain and source. Okay. So we are not changing the voltage at drain and source. We are changing only the potential at drain, means gate and source. Okay. So I have written here small wrong statement here. When we increase the VDD, then please make it correction. When we increase the VDD, then depletion at the top will not increase much beyond the pinch off voltage. But I have written wrong way. In the wrong way, when we increase the VDD, then the depletion at the top will increases much, not beyond the pinch off voltage, but it will but it will but it will increase at the bottom end, not not much than the top region. If we increase the more VDD, the potential between the drain and source will also increases. Then N channel will break down. Okay. So if we increase the more voltage at the top, at between the drain and source, you will get a constant current after beyond the pinch off voltage. After that, if we increase the more current, means more voltage, what will happen? The device will be breakdown. So you will get the infinite current. Okay. So working of the JFET. So here our aim is to compare the with case one. So what we are planning to do is so in case one we obtain the saturation current after the pinch off voltage. So we are trying to get it in the same manner. Same manner means we are trying to get the ID should be constant over the when we, even though we are increasing the potential between drain and source. Okay. So whenever so even though we are increasing the voltage VDD beyond the pinch off voltage, okay, we should get the ID current, means output current ID, drain current should be constant over the increase in the VDD. Okay, in the condition of in the case of potential between the gate and source should be negative. Okay, in case 1 the VGS means the gate and source terminals potential at the gate and source terminal should be equal to 0. In case 2 we are planning to do the VGS should be less than the 0. whatever the whatever the VDS we have used in the case 1, we should get a saturation current much earlier than the case 1. So what we are planning to get the saturation current, okay, much earlier in case 2 than the case 1. Okay, so let us example, so you have the you have applied the 4 volts in the case 1 condition. You apply then you get the saturation current. Okay, you get the saturation current ID. So we are planning to get the saturation current much earlier than the case 1. That means if when we apply the VDS which is equal to 2 volts, then we should get the voltage, means we should get the sorry we should get the output current ID much earlier than the case 1. So this is the construction of this JFET in the negative potential at the gate and source terminals. So we have given the negative potential at the to the p-type material to the both sides of the device, and positive terminal is connected to the grounded. Okay, negative terminal is connected to the also grounded to the source. The positive terminal is connected to the drain terminal. So it is in the now the device is in the reverse bias condition. When we increase the potential, so when we apply some, let us say if we apply the VDS is equal to 1 volt, okay, here gate terminal is much less than 0. So it is the width of the depletion layer will increases earlier than in the case 1. Okay, so we obtain the saturation condition much earlier in the case 2 than the case 1. So in case 2, our prime aim is to obtain the saturation at the lower value of the drain to source voltage VDS. I already said that. I repeat, in case 2, our aim is to obtain the saturation at lower values of the drain and drain to source voltage VDS. Because of this VDS, this VDS means because of the VDS in the case 2 is smaller than the VDS in the case 1. Okay, I repeat, so whatever the voltage between drain and the source is applied in the case 1, so it should be it will be greater than the volt means greater than the VDS in the case 2. So it so we can get the saturation current ID much earlier in the case 2 than the case 1. This is the I am trying to say explain it. So saturation condition is the condition in which the drain current remains constant with change in the drain to source voltage VDS. So when we change the VDS and ID remains should be constant. So we call this condition as a saturation condition. Okay. So in case 1, the VGS is equal to 0 volts and VDS is greater than the magnitude of pinch off voltage VP. Maximum drain current. IDSS means the maximum drain current. In case 2, ID becomes constant and we cannot say that ID is not equal to IDSS. So in case 1 we can say that when VGS is equal to 0 and VGS is equal to 0 and VDS is greater than the magnitude of pinch off voltage, then ID is equal to IDSS. But in the case 2, when ID becomes constant, when we cannot say that ID is no longer equal to the IDSS, we because for the IDSS VGS must not equal to must be equal to 0. So to be the ID equal to the IDSS, so VGS should be equal to 0. Okay. In case 2, VGS is negative is less than the 0 volts. So ID is not equal to IDSS in the case number 2. So make a small correction. Here is not a case 2, this is the case 1. To obtain the saturation condition in the case 2, when VDS is smaller, we need to make VGS more negative. And we are doing this to have the same width of the depletion as in the case 1. Okay. In case 1 we had a larger VDS. For that we made VGS is equal to 0, but in the case 2 the VDS is smaller. To get the same width of the depletion layer, we need to make more we need to make VGS more negative. We can I connect the negative terminal to the gate and positive terminal to the source, and the source terminal connected to the negative terminal of the potential. So simply I will explain in briefly I will explain now. So I will give the comparison between the case 1 and case 2. In case 1, the VGS is equal to 0 volts and VDSS is greater than the pinch off voltage, and also gate and source terminal is grounded, so the potential between the gate and source terminal will be 0. So when we increase the VDSS, the width of the depletion layer will be increased at the top region. It will be thinner at the bottom region, means so that near the source terminal region. Okay. So why it is increasing? Because this device is in the reverse bias condition. So in case 2 also we want to we wish to obtain the same situation, means same phenomena as like we are trying to get this same phenomena in the case 2 as like in case 1. So for that we are decreasing the potential between gate and source terminal, which is less than 0 volts, and so for applying the small potential between the VDSS VDS, so we'll get the saturation condition, which is obtained very earlier than in case 2 than in case 1. This is all about the working of the JFET. In next class I will explain about the drain characteristics and transfer characteristics, so that by the next video the JFET will be completed. Okay, so there will be a MOSFET after the transfer drain and transfer characteristics of JFET. Okay, thank you. I hope you understand today. If you have any doubts, you can ask me. Thank you.